In this lecture, we'll be discussing about the machine-level representation of built-in types in C++. So in the previous lectures, we have been studying about the primitive built-in types in C++. We have seen the signed and unsigned types in C++, and we have seen the details of the same. Now in this lecture, we are going to see how these things are represented in machine level. Alright, so let's get started. So coming to the machine level representation of built-in types, we know that computers store data as a sequence of bits, each holding a 0 or a 1. So we know that in the lower level in computers, everything is stored as a sequence of bits. Now what are bits? Bits will either have 0 or 1. So here for example, we have a sequence given here, and this represents some data. Now this sequence, if we see, it consists of just zeros and ones. Now we have to see how these bits can be used for representing various things in our computers. Now most computers deal with a memory as chunks of bits of sizes that are powers of 2. Now we see that we have a sequence of bits like this. Now in order to properly deal with them, we have to treat them as chunks of bits. That means we have to divide them into different memory locations, and we have to treat them as chunks of bits, and those chunks of bits will usually be powers of 2. And based on that, they will be represented. So let's see some examples. So here we have something called byte. Now what is byte? Byte is the smallest chunk of addressable memory, which is usually 8 bits. So 8 bits is what we call 1 byte. And byte is usually the smallest chunk of addressable memory. So here, what do we mean by 8 bits? 1, 2, 3, 4, 5, 6, 7, 8. So these 8 bits is considered as 1 byte. So that is the smallest chunk of addressable memory that we have. And we said that they are powers of 2. So we see 8 bits are used. Now 8 is a power of 2. 2 power 3 is equal to 8. So that is why we say that they are usually powers of 2. Now similarly, we have something called word. Now what is word? Word is the basic unit of storage, which is usually a small number of bytes. And usually it is either 32 or 64 bits, which is equal to 4 or 8 bytes. Now word is used to represent the basic unit of storage, and it varies from system to system that what is considered as one word. So usually it will either be 32 bits or 64 bits. Now what is 32 bits? 32 bits can be written as 4 bytes because 8 bits equal to 1 byte. So 32 bits can be written as 4 bytes, and similarly 64 bits can be written as 8 bytes. So here also we see that they are powers of 2. So 2 power 5 is 32 and 2 power 6 is 64. So we see that they are also powers of 2. So these are examples of two basic ways in which we can represent our data: bytes and words. Okay, so here we use the term addressable memory. So addressable memory means we are trying to address the memory with the help of some address. So let's talk more about the address now. Alright, so coming to addresses, most computers associate a number with each byte in memory. This is called the address. Now what do we mean by byte? We already said that 8 bits equal to 1 byte. So for each 8 bits, that is for each byte, there will be a number associated with it, and that number is what we call the address. And using that address, we will be able to access that particular data. So let's see some examples. So here for example, on a machine with 8-bit bytes and 32-bit words, we might view a word of memory as follows. So let's see. So here we have a table which shows different addresses of the different bytes that are given here. So here we are saying on a machine with 8-bit bytes, that means we are saying that in this machine, 1 byte is equal to 8 bits, and 32-bit words. That means in this machine, 32 bits are used to represent a word. Because we saw in the previous slide that it varies from system to system. In some machines, 64 bits may be considered as one word. So here we are saying that 32 bits are considered as a word. And because of that, here we see that this whole thing will be represented or viewed as one word. Why? Because we see that here we have 1, 2, 3, 4, 5, 6, 7, 8. There are 8 bits, and this is equal to 1 byte. This entire thing is equal to 1 byte, and this is the address of that byte. 736424 is the address of this byte, and similarly 736425 is the address of this particular byte, and similarly we have the addresses of this third and fourth ones. Now if I am considering a word in this memory which will consist of 32 bits, then we are considering this entire thing from this 0 till this 0. So that is an example of how addresses are used for representing the various data. So here, to make it even clearer, we see that this same table is given here, and when I say 1 bit, it means 1 bit, like for example 0, and even this is 1 bit, this is 1 bit, so all of them are 1 bit each. So this is a bit. And if I talk about byte, now byte means 8 bits together will form a byte. So I can say that this complete thing is 1 byte. Similarly, this is also 1 byte, this also, and this also is 1 byte. And these are the addresses of the different bytes. And if we say word, what is word? If it is 32 bits considered as a word, then this entire thing from this 0 till this 0, the entire thing is considered as one word. So with this, I hope you have understood how we are dividing our bits into bit, byte, and words. Now, talking more about the addresses, an address can be used to refer to any of the several various sized collection of bits starting at that address. Now, what we mean by this is that when we start counting from a particular address, and if we know the size of collection of bits that is starting from that address, then that will be used to refer to the different types, or that will help us to understand what is the data stored there. So don't get confused. We will make it clear using examples. So here, for example, we can speak of the word at address 736424 or the byte at address 736427. So here we have that same table given. We have our bytes here. We have the addresses given here. Now, I can speak of the word at address 736424. So where is 736424? Here it is. Now, if I say the word at address 736424, what do I mean? I mean the complete bits from here till here. The entire thing will be considered when I talk about the word at address 736424. Okay. Now, instead of that, if I say the byte at address 736427, what does it mean? So where is 736427? It is here. Now, if I say the byte at 736427, we are referring to only the 8 bits given over here, which is 1 byte. So 01100 That is all I am talking about if I say about the byte at address 736427. So to give meaning to the memory at a given address, we must know the type of the value stored there. So only if we know the type of the value that is stored at a particular address, then that address or that data at that memory will have a meaning. So we will explain about that in the next slide. So as I said, the type determines how many bits are used and how to interpret those bits. So we will make it clear using examples. So let's take an example here. This is the same table that we have seen in the previous slide. And here, if the object at location 736424 has type float, and if floats on this machine are stored in 32 bits, then the object at that address spans the entire word. Now, what do we mean by this? Let's see. We are considering the object at location 736424. So where is 736424? It is here. That means we are considering the start of the address as this one. Now we are saying that the object at this location has the type float. So we have already discussed about float data type. Now we are saying that here a float data type is stored, and then we are saying that floats on this machine are stored in 32 bits. That means in this particular system that we are using, for storing a float data type, we need 32 bits. Now, how many bits will be used here? Starting from here, we have to count till 32. So we have 8 here, then 16 here, 24, 32. So we have to count from here till here in order to store a float data type. So if a float is stored at 736424, we are talking about the entire word here from the beginning till the end. So we see that by knowing what is the type of data that is stored at a particular address, we can see how many bits it spans. So I hope you understood how floats are stored if 32 bits are used for storing the float data types. So it is from here till the end. Okay, now let's take one more example. So in this example number 2, let us consider the object at location 736424. So here again we are considering this starting location 7362424, and it says that the object at location 7362424 is an unsigned character on a machine using the ISO Latin 1 character set. Then the byte at that address represents a semicolon. Now what do we mean by this? Let us see. So we are starting at this address and then it is saying that it stores an unsigned character. So in the previous example, it was a float. Now in this example, we are considering that at this particular address, we are storing an unsigned character. Now we are assuming that this unsigned character takes 8 bits. 8 bits are used for representing the unsigned character. And it is on a machine using the ISO Latin 1 character set. So we will come back to this later. And then it says that that particular byte at that address represents a semicolon. Now what do we mean by this? Let us try to understand what this actually means. So as I said, we are starting at this and this is the bits that we have. So there are 8 bits which consist of this byte. Now we have to convert this bits into its decimal format and then we will see what it means. So let us first convert this one to its decimal format. So the byte is 0011111. So I'm going to make use of this rapid tables again in order to convert that binary number to its equivalent decimal number. So you can either convert it manually if you want, but for simplicity, I'm going to use this website. So I've pasted that binary value that we had 0011111. Now I click on convert and we see that the decimal number is 59. Now it was said that that machine is using the ISO Latin 1 character set. Now what that ISO Latin 1 character set means is that it is a character set and then each value will represent a particular character in that ISO Latin 1 character set table. So here I have another website which shows the ISO Latin 1 character set. So this table shows the character sets that we have. Now remember that the decimal value that we got was 59. So here the decimal values are given and the equivalent meaning is given over here of the character. So let us scroll down to 59 because 59 was the value of our byte that was converted. Now where is 59? Here is 59. So what is the value of 59? 59 actually represents a semicolon. So we see that semicolon is having the value 59. So that is what was meant over there. So coming back, so we saw that the object at location 736424 is an unsigned character. So we are using this 8 bits, that is 1 byte, to represent that unsigned character. And when we converted that to decimal, we saw that it was 59. And we saw that in the ISO Latin 1 character set, 59 represents a semicolon. So we see that we have the same data over here, but depending upon the type that it takes, we see how the value differs. So in the previous slide, we saw that if this same thing is used for representing a float type, then it was spanning the entire bits from here till here, and then that was representing some float values. But if it is used for representing an unsigned character, then starting at the same address, it is going to take only these 8 bits and it represents a semicolon. So we see that this is how the data is represented in machine level. So we see the importance of types and how the addresses will be addressed when we use different types in our programs. So with this, I hope you have understood how the various built-in types are represented at a machine level in C++. So I hope this lecture is clear to you. Thank you for watching and see you in the next one.